If you've been following multimodal LLMs, you know they're getting terrifyingly good at understanding images. But there's a hidden bottleneck. When a question requires fine-grained focus or spatial transformation, purely textual chain-of-thought reasoning falls apart. Why? Because the model has to verbally describe a visual state it can't actually draw. Small descriptive errors compound across steps, and the reasoning chain collapses. That's exactly why the field has been pushing the think with images paradigm, generating intermediate visual aids during inference to ground the reasoning process. But as it turns out, current implementations are fundamentally flawed. They're either locked into rigid, predefined toolkits, or they generate noisy, hallucinated intermediates that actively mislead the model. And critically, none of them verify whether their own edits are actually correct before using them. Today, we're breaking down ETCHR, a new framework that solves this by decoupling a dedicated, reasoning-aware image editor from the understanding model, training it with a two-stage recipe, and adding an inference time verification step that actually works. To understand why ETCHR works, we first need to look at how existing methods try to make models think with images. There are really two dominant approaches. The first is tool-based pipelines. Here, the MLLM emits structured actions, like bounding boxes, crop commands, or executable code snippets, and a deterministic renderer applies them. The problem is that the action space is fixed at design time. You can't easily ask it to redraw a maze path, reorder jigsaw tiles, or shift a 3D viewpoint. Plus, adding new tools usually requires fine-tuning the understanding model, which risks eroding its general competence. The second approach is unified multimodal models. These share a single backbone for both text and image generation, interleaving tokens natively. It sounds elegant, but in practice, the jointly optimized generative head is weaker than specialist editors. Recent benchmarks show these unified models frequently inject noise instead of guidance, and they consistently lag behind pure understanding backbones on perception tasks. Both families share a critical blind spot. They generate an intermediate image and immediately feed it into the reasoning loop without checking if it's actually valid. A single hallucinated edit can silently poison the final answer. ETCHR takes a third path. Instead of forcing the understanding model to generate edits or relying on rigid tools, they decouple a dedicated image-to-image editor from the downstream MLLM. But off-the-shelf editors aren't ready out of the box. The researchers identified two complementary gaps. First, a language side gap. Standard editors are trained as passive instruction followers. They expect explicit prompts like draw a red box around the car. They don't know how to map an abstract question like, is the car facing left or right, to the right visual transformation. Second, a generation side gap. Even when given a concrete instruction, edit correctness plummets as the reasoning depth increases. Tracing a long maze path or reconstructing a 3D viewpoint requires multi-step spatial reasoning during the diffusion transformer decoding phase, and current diffusion editors struggle to execute that reliably. ETCHR's entire architecture is built to close both gaps. The training happens in two stages. Stage 1 is reasoning imitation via supervised fine-tuning. They take a base diffusion model, Flux, Tukline base 9b, and fine-tune it to become question-conditioned. Instead of waiting for an explicit edit prompt, the editor learns to infer the necessary visual transformation directly from the question. To prevent cross-task interference, they prepend a task-level meta-prompt that acts as a soft router, partitioning the editor's latent space into task-specific manifolds. They use a large LoRA rank of 768 across all DI-T linear layers to give the model enough capacity to learn diverse transformations, from local bounding boxes to global 3D viewpoint shifts. After this stage, the editor can reliably map questions to edits, but it's still optimizing for visual plausibility, not reasoning utility. That's where stage 2 kicks in, reasoning enhancement via reinforcement learning. They don't just want the image to look right, they want it to help the downstream model answer correctly. They use Pref-GRPO, a pairwise preference extension of GRPO, with two carefully designed rewards. The first is the editing guidance reward. This measures downstream utility. If the understanding model answers correctly using the edited image, the reward is 1. It's the most faithful signal, but it's bounded by the understanding model's own capability ceiling. The second is the editing correctness reward. This evaluates the edit in isolation, using a VLM-as-Judge. It checks whether the edited image actually contains the visual evidence needed to answer the question, regardless of whether the judge can solve the full reasoning chain. This lifts the capability ceiling, but introduces judge noise. To balance them, they combine the rewards as a convex sum and soften both indicators into empirical probabilities by querying the models with multiple stochastic decodings. This reduces variance and gives the policy a much denser, more stable gradient signal. Even with this rigorous training, a diffusion model can still hallucinate. That's why ETCHR introduces an edit-verify-reason pipeline at inference time. The editor proposes an intermediate image. Then, before the understanding model reasons over it, ETCHR runs a verification step. The MLLM acts as a binary judge. Does this edit actually contain the visual information needed to answer the question? If verification passes, the model reasons on the edited image. If it fails, the system gracefully falls back to the original image. This reflection step is critical because edit errors are asymmetric in cost. A correct edit provides decisive visual guidance, but an incorrect one introduces structured confounders that MLLMs struggle to override. Filtering out bad edits early prevents catastrophic reasoning drift. The results across 5 task families, fine-grained perception, chart understanding, logic reasoning, jigsaw restoration, and 3D understanding are compelling. Paired with QN3VL8B, ETCHR lifts average pass at 1 from 55.95 to 60.77. With Gemini 3.1 flashlight, it jumps from 65.08 to 70.55. And even on Kimi K2.5, a massive 1 trillion parameter mixture of experts model, it pushes performance from 76.55 to 81.16. Crucially, it outperforms both tool-based and unified model baselines, especially on tasks requiring non-local edits like maze solving or 3D perspective shifting. Ablation studies confirm the design choices. The SFT stage alone closes most of the gap, showing that supervised imitation effectively reactivates the encoder's reasoning capacity. The RL stage adds marginal but consistent gains, particularly on perception and chart tasks where localized edits are easier for group sampling to distinguish. Combining both rewards consistently outperforms using either one alone. Correctness provides a fidelity floor, while guidance raises the task ceiling. And the verification step yields consistent gains on high-accuracy tasks like perception and charts, where suppressing harmful edits matters more than supplying noisy hints. On harder tasks like jigsaw or 3D reasoning, the gains are smaller because the baseline accuracy is so low that even imperfect edits act as useful hints rather than fatal errors. Of course, the framework isn't perfect. The authors note that GRPO's sampling granularity struggles with highly structural edits like jigsaw restoration, limiting policy exploration. ETCHR's performance is also inherently capped by the downstream understanding model's reasoning ceiling, and the image editing step does add latency compared to pure text-based reasoning. But these are engineering constraints, not architectural flaws. ETCHR demonstrates that decoupling generation from understanding, conditioning editors directly on questions, and adding inference time verification is a fundamentally more robust path for visual reasoning. It moves us past rigid toolkits and noisy unified models toward a system that actually thinks with images, verifies its own visual thoughts, and only reasons when the evidence is solid. If you're working on multimodal reasoning, spatial understanding, or agentic vision pipelines, this decoupled, verification-aware approach is definitely worth studying. The full code and paper are linked below. Thanks for watching, and I'll see you in the next one.